Good morning, good afternoon, and good evening. Take whichever one applies to you. This is my A-level complete paper 1 revision lesson. Let's get started. Beginning with 1.1.1, structure and function of the processor. Here we go. This is a diagram. This is what we're going to be talking about in this section. All the different bits and pieces that you need to know about. The control unit, or CU, sends out control signals to other parts of the CPU, for example, read or write signals to memory. Executes programs by following the fetch decode execute cycle. Contains the clock, which coordinates CPU activity and the decoder. The arithmetic logic unit, or ALU, carries out calculations and logical operations upon the data. This includes the usual add, multiply, divide, and subtract calculations, but also data comparisons such as greater than, less than, or equal to. Moving on to registers, the program counter, or PC, holds the address in memory of the next instruction. Remember, it holds the location in memory of the next instruction, not the actual instruction itself. The memory address register, or MAR, stores the address of the data that has been fetched from or is about to be sent to memory, while the memory data register, or MDR, stores the data that has been fetched from or is about to be stored into memory. The current instruction register, or CIR, stores the most recently fetched instruction, waiting to be decoded and executed. And finally, the accumulator, or ACC, holds the results of calculations and operations performed by the ALU. Buses, we all love buses. Buses are great. The address bus provides a memory address to system memory or input-output devices. The data bus transfers data between the CPU and memory or I/O devices and vice versa. And the control bus provides control signals that cause the memory or I/O to perform a read or write operation. Moving on to the fetch, decode, execute cycle. The task or the job of the CPU is to execute programs by repeatedly carrying out the fetch, decode, execute cycle. Sometimes shortened to fetch execute cycle, FDE cycle, or even FE cycle. It all means the same thing. Let's take a look at that in more detail, starting with fetch. Step 1. The program counter copies the address of the next instruction it contains into the memory address register. Step 2. The control unit loads the address to be used onto the address bus. Step 3. The control unit triggers a read signal down the control bus that causes main memory, RAM, to place the instruction being asked for on the data bus. Step 4. The instruction on the data bus is loaded into the memory data register. Step 5. The memory data register copies the instruction into the current instruction register. Step 6. The program counter can now be incremented by 1 to point to the next instruction, and the fetch stage is now complete. The decode stage. The contents of the current instruction register are sent to the control unit. The control unit then decodes the instruction. The execute stage. The instruction within the current instruction register is carried out or executed by the CPU. Registers can be changed in different ways during the execution phase, depending on the instruction. If a memory location is to be read from or written to, that is an LDA or STA instruction in the little man computer, then the address stored within the current instruction register will be loaded into the memory address register. In the case of the STA or store operation, the data stored in the accumulator is sent to memory. In the case of a load or LDA instruction, the data is loaded from memory into the accumulator. If the instruction is to carry out a calculation, that is an add or a sub operation, then the contents of the memory data register and the accumulator are sent to the ALU and the results sent back to the accumulator. Next, we have the factors affecting the performance of the CPU, starting with clock speed. A clock in the control unit sends a pulse at fixed intervals to control the speed that the CPU carries out the fetch, decode, execute cycle. The higher the speed of this pulse, the more instructions can be completed per second. Overclocking. Some CPUs allow the clock speed to be altered. This can result in faster performance because the CPU can carry out more instructions in the same amount of time, but generates more heat and could damage the CPU. Cache. Cache is a small amount of very fast memory built into the CPU. It holds instructions or data that are frequently used, have recently been used, or are about to be used. It is faster for the CPU to fetch data from cache rather than from the slower RAM. That's the von Neumann bottleneck in operation. However, cache is expensive, more expensive certainly than RAM. Number of cores. A core is a complete processing unit. It has its own control unit, ALU, registers, etc. Each core can independently carry out the fetch, decode, execute cycle. This allows multiple instructions to be processed at the same time. The use of pipelining. Pipelining is a technique for fetching an instruction while the prior one is being decoded and the one before it is being executed. It is a simple form of parallel processing. So you can see from the table here, during step 1, we can fetch instruction number 1. In step 2, we can fetch instruction 2 while at the same time decoding instruction number 1, and then at the next stage, we can fetch instruction 3 while at the same time decoding instruction number 2 and executing instruction number 1, and so on and so forth. A pipeline controller has to predict jump instructions in order to keep the pipeline full. If the controller makes a mistake, the pipelines have to be emptied or flushed, which degrades performance. Von Neumann, Harvard, and contemporary processor architectures. The von Neumann architecture has a single control unit and a single ALU. It works sequentially through instructions, stores instructions and data together in the same memory unit, in a binary format. The Harvard architecture, well, the idea of the Harvard architecture is to split the memory into two parts. One part for data and another part for programs. Each part is accessed with a different bus, and this gives certain advantages over von Neumann architecture. However, it's more difficult to design and build, and more difficult to program, and generally more expensive. Modern architecture makes use of parallel processing, processing more than one piece of data at the same time. This includes something like pipelining, which we've already discussed, array processing, which is an example of SIMD, single instruction multiple data. Here, a number of ALUs allow one instruction to be performed on a large data set simultaneously. An example of array processing would be a graphics card or something similar. We also have multi-core processing, which is MIMD, multiple instruction, multiple data. Here, each CPU has a number of cores, which are complete processing unit, or each computer system has multiple CPUs, for example, a workstation or a supercomputer. Next up, we have types of processor. We'll start this section with CISC and RISC processors. CISC, complex instruction set computing, supports more instructions, which requires more transistors and a larger physical size, therefore requiring more power and generating more heat. But the more complicated hardware means the software is less complicated. Compilers are easier to design for CISC systems. RISC, reduced instruction set computing, supports fewer instructions, which requires less transistors and a smaller physical size, requiring less power and generating less heat. RISC instructions usually take a single clock cycle, meaning pipelining can be used with maximum efficiency. The simplified hardware, however, means that the software is more complicated. GPUs and their usage. GPU stands for Graphical Processing Unit, and this is something that is specifically designed to perform the calculations associated with graphics. It is an example of an array processor, which means it has a number of ALUs to allow a single instruction to be performed on multiple items of data at the same time. Sometimes this would be called a SIMD, or Single Instruction Multiple Data System. While designed for graphics, for example gaming, animation, computer-aided design, GPUs are increasingly being used in many other fields. So some examples: modeling physical systems, audio processing, breaking passwords, cryptography, cryptocurrency generation, machine learning, all that other sort of stuff. Multi-core and parallel systems. Parallel processing is the simultaneous processing of data. Parallel processing can be considered to be a non-von Neumann architecture. There are a number of different ways to do this depending on the use, and this brings us back to SIMD and MIMD. Again, single instruction, multiple data. Here the same operation is carried out on multiple pieces of data at one time, so for example with a GPU. Multiple instruction, multiple data means that different instructions are carried out concurrently on different pieces of data. This can be achieved by having a number of cores inside a CPU, a multi-core system. A problem can then be divided up and run in parallel amongst these cores. MIMD takes place on a much larger scale on workstations and supercomputers. These can have multiple CPUs, with each CPU consisting of multiple cores. We can also do this with distributed computing, where multiple computer systems are connected together via a network to work on a problem. 1.1.3 Input, Output, and Storage. So input and output. This is quite simple. Input devices allow data to be entered into a computer. So for example, a keyboard, a mouse, a microphone, a scanner, a joystick. While output devices allow information to be retrieved from a computer. Examples include printers, speakers, monitors, actuators, etc. You are not expected to know the detailed working of any of these sort of devices for the examination, but you're expected to be able to choose a suitable input and output device for a given scenario. Please do not be that student that gets the input and output confused in the exam. Storage devices are used to hold data and programs for the long term. They are all non-volatile. Storage devices fall into three categories: magnetic, flash, and optical. When looking at storage, there are many considerations. Cost: how much does it cost to be purchased per gigabyte? Speed: how quickly can it be read from and written to? Capacity: how much data can it store? Durability: how likely is it to be damaged or break? Reliability: will it retain the data safely for a long time? Will it break with wear and tear over time? Magnetic storage uses magnetizable material. Patterns of magnetization are used to represent binary sequences. Examples include hard disk drives and magnetic tape, sometimes still used to archive data. Magnetic storage tends to have high capacity at low cost. However, it is vulnerable to magnetic fields and X-rays. Also remember that hard disk drives, or HDDs, have moving parts, so they are vulnerable to shock, so for example being dropped or moved suddenly. Optical storage, such as CDs, DVDs, and Blu-rays, work by using lasers. Sounds very futuristic, but this sort of technology is becoming slightly outdated, but you do still need to know it for the exam. Optical media tends to be cheap to mass produce and distribute. It is fairly reliable as long as it's not scratched or broken. That's why with CDs and DVDs, etc., you usually have a case so you can store the disc safely. And you have multiple varieties. A CD, you're looking at about 700 megabytes of storage. DVD is about 4.7 gigabytes, while a Blu-ray disc can be anything from 25 gigabytes to 100 gigabytes or more, depending on what technology you're using, dual-sided, dual layer, that sort of thing. Flash memory works by using a special type of solid-state memory that is both non-volatile and can be overwritten. Examples include memory sticks or memory cards, solid-state drives, SSDs, and modern ROM chips. Advantage: can be read from and written to at high speeds, and as it has no moving parts, has lower power consumption, and is unaffected by sudden movement or shocks. Disadvantage: it's more expensive per gigabyte than magnetic storage. You also have a limited number of erase write cycles, but that number is actually very high and isn't really applicable to a home user. But if you're an enterprise user, you will have to replace all the drives eventually. RAM and ROM, the classics. You've always got to know your RAM and your ROM. RAM is random access memory, and it's a type of primary memory where programs and data being run by a computer are temporarily stored. So for example, the parts of the operating system that are currently needed, programs that are currently running, any data those currently running programs require. ROM is read-only memory. It is a form of primary memory that can be read from but not written to. As ROM retains its contents where the power is lost, it is referred to as being non-volatile. A common use for ROM on computers is storing the BIOS, the basic input-output system. Holds the instructions to boot the computer and initialize hardware. On embedded systems, the firmware in ROM may act as the device's complete operating system. Virtual storage is sometimes known as cloud storage. In fact, it's probably called cloud storage more often, but the exam board like to call it virtual storage. Please do not confuse this with virtual memory. This type of storage is based around the concept of storing data over the internet instead of on a local storage device. Has grown a lot more popular in recent years thanks to the growth of internet access and speed, and also the growth of 4G and 5G mobile networks, so you can get access to your data on the go. Advantages of virtual storage. Data can be accessed from any location, as long as you have the internet access, obviously. Data can be shared easily between people and devices. Capacity can be considered limitless from the point of view of the user. Increased storage can always be purchased. And the capacity is scalable to the needs of the user. You can have more one month and less the next. Backing up the data and security are no longer the concern of an individual user or business. You can let a big professional company take care of it for you. Disadvantages. You need a fast, reliable internet connection. Can get expensive if you need to store very large amounts of data. And you need to trust the company running the service. How good is their security? Do they have multiple backups in different locations? Do they comply with necessary laws? Moving on to the next section, we have 1.2.1 System Software. The need for, function, and purpose of an operating system. Well, basically, an operating system, or OS, is the software that manages the computer hardware and software. Modern operating systems have several purposes, including to manage the hardware/peripherals, provide a user interface, provide a platform to run other software, manage the security of the system, manage CPU usage through scheduling and interrupts, provide utilities for system maintenance, and manage available memory. Memory management. Memory, RAM, is a finite resource and must be managed by the operating system. The memory manager controls the allocation of random access memory to each running process. If the memory manager fails to manage memory well, then the computer will slow down and might crash. The memory manager must also control virtual memory so that programs and data can be loaded and run even when the physical RAM is full. Interrupts. Sometimes hardware or software needs to get the CPU's attention immediately. Polling. Here the CPU regularly polls or inquires if a device needs attention. This is inefficient because usually the answer is no. A more efficient solution is interrupts. If a hardware device or application needs attention, it raises an interrupt with the CPU. Technically, if it's an application, it's software, so it's raising it first with the operating system. If this interrupt is of a higher priority than the current task, the relevant ISR or interrupt service routine is run. If there are any interrupts and they are of higher priority than the current task, then the following steps are carried out. The contents of the program counter and the other registers are copied to an area of memory called the stack. The relevant interrupt service routine can then be loaded by changing the program counter to the value of where the ISR starts in memory. When the interrupt service routine is complete, the previous values of the program counter and other registers can be restored from memory to the CPU. And yes, before you ask, an interrupt can be interrupted by another interrupt. At the end of each iteration of the fetch, decode, execute cycle, the processor checks to see if there are any interrupts. So we can say fetch, decode, execute, and actually check for interrupts before fetching the next instruction. Scheduling. A scheduler or schedule manager is the part of the operating system that uses a scheduling algorithm to determine how to share processor time. Remember, even on today's multi-core systems, you'll have a lot more processes running than you have cores. So the whole usage of the CPU has to be shared between multiple running applications. How it does this? Well, there are lots of different ways, and I'll give you a brief rundown. Round robin. In round robin scheduling, each process is given a fixed amount of time. If it hasn't finished by the end of that time, it goes to the back of the queue. First come, first served. Similar to round robin, except each process is allowed to run to completion. Shortest job first. Shortest job first picks the job that will take the shortest amount of time, measured in estimated FDE cycles, and run until it finishes. Shortest remaining time. The scheduler estimates how long each process will take. It then picks the one that will take the least amount of time and runs that. If a job is added with a shorter remaining time, the scheduler switches to that one. And then we have multi-level feedback queues. This takes into account the priority of a task by maintaining queues with different priority levels. If a process is in, say, the low priority queue for too long, it will get moved up so that eventually all processes will get a chance to be processed. There are many different types of operating system used in many different capacities. And often individual operating systems can borrow different parts from different types of operating system. So there's not strictly one type or the other. You can kind of blend these together, and you'll see that when we go through them. A multitasking operating system is one that is designed to allow the user to do multiple things at the same time. A multi-user operating system allows the user to share the resources of one powerful machine, for example, a supercomputer. Distributed operating system is one that runs across lots of individual computers, but appears to be one system to the end user. An embedded OS, one usually found in a piece of hardware that serves a single purpose, and a real-time operating system reacts to input as close to real-time as possible. Device drivers contain software that tell the operating system how to understand the data coming from an external hardware device and what format it expects to receive the data in. BIOS is your basic input-output system. This controls the startup sequence of the computer and also helps configure hardware devices. Virtual machines. A VM or virtual machine is a program designed to fully simulate a computer, but in software. It is a simple way to run more than one operating system on the same computer. Or a very powerful server can be split into several smaller virtual machines to use its resources better. It can also help with security. If the virtual machine is affected by a virus or another nasty piece of software, the host operating system is unaffected. There are also virtual machines designed to run intermediate code from a specific computer language, for example Java. Now let's move on to 1.2.2, Applications Generation. Application software is software that allows a user to perform a task or produce something. For example, a word processor, a spreadsheet, a web browser. You may have to recommend an application and justify it for a given scenario. Use the generic name in the exam, not the name of a particular product. So please recommend a word processor, not Microsoft Word. A utility is a small program that has one purpose, usually concerned with the maintenance of the system. For example, disk cleanup, defragmenter, compression, encryption. Make sure you're familiar with the key types so you can justify recommending one for a given situation. Open source versus closed source software. Open source software means that the source code for the software is available. Usually the software is free, can be amended by the user to add features and fix bugs. This is said to encourage collaboration and rapid development. Closed source software, on the other hand, means that the source code is proprietary and is not available. Usually more polished than open source software, often easier to install and easier to use with a more attractive user interface. Usually comes with a warranty or guarantee of some sort, and often has customer support available. Translators. A translator converts source code into machine code. There are three types: assembler, interpreter, and compiler. An assembler converts assembly code into machine code. Interpreter converts high-level source code into machine code line by line, good for use during coding and debugging. A compiler converts high-level source code into machine code all in one go. This can take a long time, but afterwards it can run without the need for source code or a translator, so it's faster. What happens when your software is compiled? Let's take a look at the stages of compilation. First of all, we have lexical analysis. Here, comments and whitespace are removed from the program. The remaining code is turned into a series of tokens. A symbol table is created to keep track of the variables and subroutines. We then move on to syntax analysis. This will produce an abstract syntax tree that will represent the program. It checks that the code has been written using a valid syntax. Code generation optimization. Code generation is when the compiler converts the output of the syntax analysis into object code. Compilers can be tweaked to optimize for either speed or memory, as it is often difficult to optimize both at the same time. Libraries contain existing code that developers may wish to reuse. Linkers are used to incorporate library code into the final program. And a loader is the part of the operating system responsible for loading an executable file into memory. Now the bit that you're all waiting for, 1.2.3 software development. Software development lifecycle methodologies. A process for planning, creating, testing, and deploying high-quality software. We need to know the waterfall lifecycle, rapid application development or RAD, spiral model, and agile software development. Starting with the waterfall model. This divides the process into sequential stages which are followed in a linear fashion. This works well when there is a clear expected output at each stage and everyone has clear responsibilities. Tends to suit large-scale projects with stable requirements. If the project requirements change, this model is inflexible and cannot respond easily. No working software is produced until late during the life cycle, so problems may not be discovered until it is too late. The waterfall life cycle is not suited to high-risk or complex projects. The rapid application development model involves building a prototype. This is evaluated and refined over multiple iterations until it becomes the final product. RAD is well suited to projects where the requirements aren't entirely clear from the outset. Allows the product to be made and put to market extremely quickly compared to, say, the waterfall model. The end product is likely to have excellent usability, but it does require a heavy input time from the client to give feedback and guide the project. RAD does not scale well and is less suited to large projects with big teams that will take a long time to develop. The spiral model is designed to manage risk and requires risks to be identified and evaluated at each stage. So it manages risk well and is flexible and is perfect for large-scale or risky projects. However, it requires a high level of expertise in risk analysis. Good risk analysts are expensive, which adds to the cost of the project. It is also complex. There are many stages to pass through, so it's very time-consuming. Agile methods are designed to deal with projects where there may be changing requirements. One form of Agile is extreme programming, or XP. This is an Agile method where the focus is on producing extremely high-quality code. Each iteration in XP produces a version of the system with code of good enough quality to be used in the final product. This can involve pair programming. The quality of the final code is therefore likely to be very high. The project, however, can be too code-focused and not design-focused, so may not be the best possible product. And XP also produces little or no documentation. Algorithmic thinking is key to solving any problem, not just those related to computers. An algorithm, as you should know by now, is a set of instructions to solve a problem. This could be a computer program or a recipe for your favorite meal. We often use pseudocode or flowcharts to represent algorithms. 1.2.4 Types of Programming Language. Programming paradigms. A common way of grouping languages together is by their general approach to problem solving, what we refer to as their paradigm. These approaches are often specialized. They focus on one aspect of programming at the expense of others. Each paradigm offers advantage over other types, and each one, of course, has some limitations. There is not one paradigm that's the best. Each paradigm is very good in certain situations. Very roughly, we can divide the classes of programming language into low level or high level. Low level can include things like machine code and assembly language. High level can be subdivided into imperative and declarative languages. We can divide imperative into procedural and object-oriented, and those are the ones you probably have most experience with. If we look at the declarative languages, we can have declarative logic and functional languages, which are maybe a little bit more exotic. Low-level languages are those directly linked to the architecture of the computer. Machine code and assembly language are low-level languages. Low-level languages are excellent for close control of the CPU. For example, many device drivers are coded in assembly language. They can be very efficient. Well-optimized code written in a low-level language can be made to run very quickly compared to other programming languages. A high-level language is one designed to be closer to the way we express ourselves, using a mixture of English words and mathematical expressions. Imperative language, well, imperatives means to give orders or instructions. So these languages are all about the computer being told what to do step by step. And we often subdivide this into procedural and object-oriented. Declarative languages, these tell the computer the qualities of the solution that we're looking for, but not how to compute it step by step. And here we can have logic and functional languages. Procedural. Instructions are given in sequence. Selection is used to decide what a program does, and iteration dictates how many times it does it. Programs are broken down into key blocks called procedures and functions, hence the name procedural. Examples of procedural languages include BASIC, C, Pascal, etc. Object-oriented, a programming style in which a solution consists of objects that interact with each other. Examples of object-oriented languages include Java, C++, C#, etc. Declarative logic, designed for applications such as AI, where deductions need to be made based on a set of rules. Examples include Prolog. Functional, these are designed for the original purpose of computers, calculating. So these can be used for mathematical and simulation applications. Some examples might include Lisp and Wolfram. Next up, we have assembly language. Assembly language is a big topic. I could easily spend an hour talking about assembly language in detail and what you need for the exam, but this is just a basic refresher on the next few slides. While machine code uses binary instructions to represent instructions, what we call opcodes, and the data they use, operands, assembly uses mnemonics that are easier for people to remember. As each assembly code instruction represents a machine code instruction, assembly code programs can often be much longer than their high-level equivalents. So over here we have the little man computer instruction set that you need to know for your test. The little man computer is a very simplified version of a computer that only has a very limited instruction set. Obviously, if you're programming in modern assembly language, for example, x86 or RISC platform, you're going to have a lot more instructions. I think the exam board just want to know that you can do the basics. So I'm going to take a look at two programs and just take you through how they work line by line. First of all, we have a very simple program that just adds two numbers together and outputs the result. Line 1. A number is entered and stored in the accumulator. That's what IMP does, IMP. Line 2. The contents of the accumulator are stored in a memory location labeled num. Line 3. A number is entered and stored in the accumulator. This will overwrite the previous entered value. So if you haven't stored the value of the accumulator into memory, it will be lost when you input another value. Line 4. The value held in the memory location labeled num is added to the value held in the accumulator. 5. The value in the accumulator is output. So out means output, nice and simple. Line 6 is HLT or halt, so the program ends. And then line 7, we've declared that we're going to use a location in memory and we're going to label it as num. So these are kind of like our variables. We declare them though at the end of the program, not at the start like we usually do in high-level languages. So I'm going to be taking a memory location and I want to refer to it as num. So I'm going to declare that at the bottom of my program and then I can use it in the rest of my program. Now we have a more complicated program. This program compares two numbers that are input and will output the second if it is bigger, otherwise it outputs the first. So basically it's doing a comparison and deciding which of the two numbers input is the biggest and then outputting it. So line 1, a number is entered and stored in the accumulator. Line 2, the contents of the accumulator are stored in a memory location labeled first. Line 3, a number is entered and stored in the accumulator. Again, this will overwrite the previous entered value, but that's okay because I have stored it in memory. Line 4, the contents of the accumulator are stored in a memory location labeled second. Line 5, the value held in the memory location labeled first is subtracted from the value held in the accumulator. Note the order of the subtraction there. Line 6 is starting to get a little complicated. If the value held in the accumulator is 0 or positive, jump to the location labeled second big. Line 7, fetch the value held in the memory location first and store it in the accumulator. Line 8, the value in the accumulator is output. Line 9, always jump to the location labeled program end. Line 10, start with a label that could be jumped to from elsewhere in the program. Fetch the value in the memory location second and store it in the accumulator. 11, the value in the accumulator is output. Line 12 starts with a label that can be jumped to from elsewhere in the program. The program then ends. And then we have declared our two memory locations that we want to use. We're going to have a memory location labeled first and another memory location labeled second that we can use to store values throughout our program. If you find this a bit confusing, go to the Little Man Computer website, type it in, run it, see what's happening. Do a bit of experimenting. Modes of addressing memory. Memory address modes determine the method used by a running program to access its data or the next instruction. If you're programming in a high-level language, then you don't really have to worry about this. But if you're programming, for example, in assembler, then you do have control about which addressing mode that you use. The ones we need to know about are immediate addressing. Means that the data to be used is hard-coded into the instruction itself. The operand is the data. Direct addressing. Here the operand contains the memory address telling the CPU directly where to look. Indirect addressing means that the address of the data is held in an intermediate location, so that the address is first looked up and then used to locate the data itself. Indexed addressing means that the final address for the data is determined by adding an offset to a base address. This is what we could use for something like an array, for example. Now let's look at object-oriented languages. So again, this is another huge topic. I could spend hours talking about this. Again, we're just going to revise it, just give you a few key points on a few slides. Object-oriented languages, OO, is a style of programming where we try to understand a computer program in the same way that we understand real-world objects. It is a programming language model in which programs are organized, so Z instead of an S there, American spelling, in which programs are organized around data or objects rather than functions and logic. Sometimes referred to as OOP, object-oriented programming. An object can be defined as a data field that has unique attributes and behavior. The main idea for object-oriented languages is to gather the data, what we call attributes, and all the functions, methods, that act upon that data into one entity called a class. So making data hiding, through encapsulation and abstraction, code reuse, through inheritance and polymorphism, and maintenance much easier. Object-oriented programming, OOP, relies on objects in the real world being classified. Now remember, a class is just a template, a cookie cutter. It is used to define what attributes and methods objects of a certain type should have. All classes have three main sections: a class name, attributes, all the information generic to that object, and methods, the procedures and functions that allow you to access and manipulate data. So over here you can see we've created a class called dwelling, and it represents where somebody lives. So the class name is just dwelling. All dwellings need an address and a number of rooms. And the methods that we require are going to be output data, get address, and get number of rooms. This is very simplified, of course. Again, you'll notice this is just a template. There's no actual information stored. It's just the structure of what the data is going to look like. We then use the class to create or instantiate new objects. So we can have different dwellings with different attributes that can access their methods. Here we'll have a look at the entire dwelling class written in pseudocode. So this isn't C++ or C# or Java, it's just the OCR pseudocode just to make it nice and easy for everyone to understand. We start with the name, in this case class dwelling. We then declare the attributes. So again, these are just variables. We have the keywords private or public. Attributes are typically private. That means we can use encapsulation. The data is not accessible from outside the class. We then move on to our constructor. We know that that's a constructor because we're using the keyword new. Obviously, it has to be accessible from outside the class, so it is declared public. It takes in the values that we require, so we can set those attributes to the values that we need to hold. We then have the methods, the procedures and the functions that we require in this class. Again, you can just write them like you would any procedure, any function. Just remember, typically they will have the keyword public because often they'll be accessed from outside of the class. Then we can use this to create new objects by instantiating them just like this. Again, we're using that keyword new and the name of the class here. Often just simply being able to instantiate a simple object in the exam can be worth 2 or 3 marks. Some more keywords. Abstraction. Objects only reveal internal mechanisms that are relevant for the use of other objects, hiding any unnecessary implementation code. This concept helps developers make changes and additions over time more easily. Encapsulation. The implementation and state of each object can be private. This characteristic of data hiding provides greater program security and avoids unintended data corruption. This can be an advantage of OOP over procedural languages. Inheritance. This is the concept in which we define a class which inherits attributes and methods from a parent class. This encourages code reuse in programming. Polymorphism. The ability to use the same code to process different objects according to their type. The program will determine which meaning or usage is necessary for each execution of that object, cutting down on the need to duplicate code. 1.3.1 Compression, Encryption, and Hashing. Compression. When transmitting files, storing very large number of files, or storing a large number of files, we need to compress the data to make it smaller. There's 2 main types, lossy compression and lossless compression. With lossy compression, you're removing data to reduce file sizes, whereas with lossless compression, there is no data loss. Lossy compression achieves more compression than lossless. However, lossy compression, you are resulting in a reduced quality compared to, say, lossless, where there is no loss of quality. With lossy compression, it depends on the kind of fault tolerance of human sensors sometimes. You might notice this, you might not. But with lossless, obviously, you never have that loss of quality. Lossy compression is irreversible. The discarded data cannot be recovered, whereas with lossless compression, it is reversible. The exact uncompressed data can be recovered. Here we have a little table just taking you through the basics of lossy and lossless compression and some key information that you need to know. To go into it to a little bit more detail, let's look at a couple of forms of lossless compression. First of all, RLE, or run length encoding. This replaces repeating consecutive sequence of data with a single data value and a count of how many times that data value occurs. For example, if there's a sequence of 100 blue pixels in an image, this could be encoded as blue, B for blue, 100. This process works best if there are long sequences of the same data. However, small files without long sequences of repetition may end up being larger after compression. In the image below, there are 144 pixels with a color depth of 8 bits per pixel. So the uncompressed image size would be 144 bytes. After run length encoding is applied, the size would be 70 bytes. We can further take run length encoding and apply it at bit level. Another form of lossless compression is dictionary coding. This makes use of redundant repeated data so that if a data item occurs multiple times, the item is stored once in a dictionary and then the position of that data is also stored. The best savings are in long files with lots of repeated data. Small files with little repeated data may end up being longer after compression. Considering the following sentence, if you're not fired with enthusiasm, you will be fired with enthusiasm. The original text is 70 characters, and let's say 1 byte per character. We can then use this to build a list of unique words of the text. So we have our dictionary, and to store the dictionary, let's say, is 36 characters. We can then store the text just as the sequence of numbers representing the order of the words. The new text, well, we have 36 in the dictionary, 26 in our list. I have to include spaces there obviously as well, and that gives us 62 bytes. But we've gone from 70 to 62, which is a reduction of about 11%. Now remember, the original can still be reconstructed exactly. No data is lost. For larger blocks of text with many repeated words, this could reduce the size of the file considerably. Encryption is the process of scrambling data in such a way that only legitimate and authorized users can read it. In symmetric encryption, the same key is used to encrypt the message and also decrypt it. This works well when you can physically give the key to another person, so you know that it's been passed securely, and then you can then pass messages and data to each other that can be decrypted easily. Asymmetric encryption, however, requires the use of two different keys. This makes it much better for use across something like the internet, where two computers cannot meet and securely exchange keys. The key used to encrypt the message in this case is not the same as the key needed to decrypt it. One of the keys is publicly known and is used to encrypt messages. A second key is kept private and is used to decrypt the message. If you have the scrambled ciphertext and you have the encryption key, you cannot decrypt it. You can only decrypt it if you have the private key. This is sometimes known as a public-private key system. Hashing is generating a value or values from a string of text using a mathematical function. This is a one-way process that scrambles data. If we apply a hashing algorithm, for example SHA-256, to the opening chapter of A Tale of Two Cities, we get something like this. Some uses of hashing include faster searching. Hashing can be used to speed up searching a database. If you store an index of hashes, users can search for the shorter hash rather than the longer data. We can use it to verify the integrity of files. Hashing can be used as a digital fingerprint to verify the integrity of files. You can run a hashing algorithm on a downloaded file to see if it matches the one provided. We can also use it to help encrypt passwords. When a user chooses a password, it is subjected to a hashing algorithm that transforms it into a fixed length hash value. This, not the password, is then stored on the server. So the password list is stolen, it will not grant access. So if you type the hash directly into the password field when you're logging in, obviously it'll run the hashing algorithm on that and it'll come up with some gobbledygook that doesn't match what's stored in the database. Possible issues with hashing algorithms. Data collisions. The algorithm has to ensure there's a low risk of different files producing the same hash. Calculation time. There's a computational overhead for hashing, and if this is too high, it may discourage usage. This is why in the past, and even sometimes in the present, proper hashing isn't done on passwords that websites store. Size. The algorithm has to produce hashes that are smaller than the original file, otherwise there's no point in using it to make comparisons. Next up, we have 1.3.2 databases, fun for the whole family. A database is a structured, persistent collection of data. A flat file database is where all the data is stored in one large table. This is easy to set up and can be created in software such as Excel, so spreadsheet software. The main problem with a flat file database is redundant data, data that is repeated needlessly. A relational database is where the database is stored in separate tables that are linked together through the use of primary and foreign keys. So here is a simple database for a school library. At the top here you can see the flat file system. All the fields, all the records, everything is in one table. you can see there's a lot of repeated data there. If you wanted to update somebody's phone number or a book title or a name, it would be quite difficult to make sure it's updated everywhere consistently. Whereas with the relational database at the bottom, you have 3 tables: students, borrows, and book. The tables are linked together through the use of primary and foreign keys. So member ID links student and borrows, and book ID links borrows and book together. Some more vocabulary. A primary key is a field within a database which enables every record to be uniquely identified. Foreign key is used to link tables together, a field in one table that is linked to a primary key in another table. Secondary key is made on a field that you would like to be indexed for faster searches. A table can have more than one secondary key. We model entities and relationships by means of an entity relationship diagram, sometimes referred to as an ER diagram. There are 3 types of relationship between entities. We have one-to-one, one-to-many, and many-to-many. If you're drawing this in the exam, pay particular attention to the relationships to make sure you get them right. It's very easy to make a mistake here. Many-to-many relationships should not exist in an efficient relational database. They break the rules of normalization that we'll look at later. If you have a many-to-many relationship, a link entity needs to be added. This is an entity that sits between the 2 current entities and has a one-to-many relationship with each. So we have students and courses. We can transform that so we have students linked to registration, which links to courses. Actor and films can be changed so we have this cast entity in the middle. So actor to cast has a one-to-many relationship, and cast to film has a one-to-many relationship. Again, it's always going to look the same as this pattern. One-to-many, many-to-one. It's always going to be the same when you draw it like this. Capturing data. Before setting up a database, the data must be collected. The data entered into a database must be accurate. We have the expression garbage in, garbage out for a reason. Methods may include data capture forms. Could use optical character recognition, OCR, to speed up the capture process. We could have web forms that we're very familiar with filling in. Barcodes, QR codes, magnetic stripes, etc. Selecting data. Well, we'd often use SQL for that, structured query language. This is a common query language for all databases, which allows data to be extracted from a database. A user may also be presented with a graphical interface to help sort and filter the data depending on their database management system. Managing data. The database management system provides a layer of abstraction between the user or database designer and the data. The DBMS hides the underlying structure of how the data is stored, enforces data integrity rules, and provides secure access and encryption. SQL is both a data definition language and a data manipulation language. It can be used to modify the data, creating and changing tables, adding records, deleting data, etc. Exchanging data. Often we need to exchange data between databases and other applications, and there are a variety of different ways to do this. Now in the exam, you're unlikely to be asked specifically about one of these methods. However, you do need to be able to describe 1 or 2 for use in a certain situation. So whether it's XML or JSON or SQL or CSV files or APIs or electronic data interchange, you want to probably memorize 2 or 3 of these just so you can talk about them in an exam if you need to. Now moving on to normalization to third normal form. I'm going to spend a little bit more time on this just because I find this is something students often struggle with when we do revision lessons in school. Normalization. This is a process where a collection of data is gradually organized into tables in a series of steps. Each step leads to what we call a normal form. For your A level, you need to understand up to 3NF, third normal form. 0 normal form, this just means the data is not normalized yet. It's just a very basic flat file database. All the fields are in one table. First normal form. To decide whether the data is in 1NF, you must check that the data conforms to the criteria listed here. Each record must have a primary key. Remember, this is a single attribute or combination of attributes for composite primary keys that could be guaranteed to be unique. 2. The data in each field, each column, must be atomic. This means a field contains a single value that cannot be sensibly subdivided. 3. Each record must have no repeating groups of attributes. A set of attributes that appear more than once within the record, not the table, is a problem. And 4. Each field must be unique. Repeated or similar columns should be removed. Second normal form. To decide whether data is in second normal form, 2NF, you must check the data conforms to this criteria. First of all, the data should be in first normal form. And then 2, there should be no partial dependencies. Partial dependencies arise where a table has a composite primary key. Check that all non-key fields depend on the entirety of the composite primary key. A sign that data is not in second normal form is data sets that occur in multiple rows. If you do find there are partial dependencies, split the table on that attribute and move to a new table. Create relationships between these new tables and earlier tables by means of foreign keys. Third normal form. For a database to be in 3NF, well, got to check the data is in second normal form first, and then we have to remove any columns that are dependent on non-key fields and not on the primary key. There must be no non-key or transitive dependencies. Call them what you want, it means the same thing. For third normal form, check that each non-key column is dependent on the key, the whole of the key, and nothing but the key. So let's have a look at an example here. So we've got a little database here. We can look at it and go, is this in first normal form? Well, let's have a look at our criteria. Each record must have a primary key. Yep, it's got a primary key. The data in each field must be atomic. Nope, that is not true. Student name is not atomic. Each record must have no repeating groups of attributes. Well, again, that's not true. Each record has multiple subject numbers, subject names, etc. within it. Can't have that. Is each field unique? Yep, it is. So it works on that field. So 2 and 3, it fails the test for first normal form. To make it first normal form, we must make student name atomic, separating forename and surname. We must also remove all duplicate values by creating separate rows for each instance of a subject. And we have this. Now we can make a composite primary key now by combining student number and subject number together. So you can see they're both underlined. That is the composite primary key. Now we have to decide, is it in second normal form or do we have to make any changes? Well, let's have a look at it. Forename, surname, and address depend only on half of the primary key, which is student number. On the other hand, subject name, teacher number, and teacher depend only on subject number. A sign of this is there's a lot of repeated data in the records. So again, to make it second normal form, we have to make some changes. We create two tables. Both are linked together by means of the foreign key student number. So student number is obviously a primary key for student, and we can all use that to link to the correct subject in the subject table. We have a problem though. One student can take many subjects. One subject can have many students. We've ended up creating a many-to-many relationship, and we want to not do that. So we need to create another entity, another table, to join these two together. Go from student to subject, student to registration to subject. In the exam, what you call that new third table doesn't really matter. Just give it something sensible. But remember, it's a one-to-many relationship between all the tables here. So now we can link all three tables together by the use of foreign keys. So student number will link to the student table and subject number will link to the subject table. We still have a problem though if we're in third normal form because subject is not fully normalized. We have transitive dependencies because not all details on this table are dependent upon the primary key. Teacher depends on teacher number, not subject number. So we need to take normalization a step further and eliminate any non-key dependencies. So now we have a teacher table, and teacher number links both tables together. So now we have third normal form. And everybody's favorite, SQL. I really do like SQL. I think it's really simple to get marks for SQL in the exam if you know it well enough. You do have to spend a bit of time on it, not make careless errors that students often make. But if you've got some good understanding of this, it's really a good way to pick up marks in the exam. So what do we need to know for SQL? We need to know the basic code. Select from where. Select your field names from the table name where a condition occurs. Don't get your field names and your table names mixed up. That happens all the time. Always remember the order. Select from where. You can do it in 1 line, 2 lines, 3 lines. Doesn't matter as long as you get the keywords in the right order. So the example here is select forename, surname from student where grade greater than 50 and year equals 12. Don't think that's too difficult, but again requires just that little bit of practice and confidence. We also need to use wildcards. If we are selecting all the field names, we don't have to list all of them. We can just use the asterisks. And we can also use the percentage sign to represent 0, 1, or multiple characters. So for example, select all the fields from student where surname like, and then in speech marks, A and a percentage sign. So it starts with A and then has characters after that. We can use select statements within select statements to perform more complex queries using nested selects. Again, this is something that students can find difficult if they haven't got a bit of practice. The query below returns all the students of a grade higher than the student called Smith. This query can look a little difficult to start with. Select name from student where grade greater than, select grade from student where surname equals Smith. So what we need to do is start with the inner select first, the bit that's in brackets. We want to find all the students of a grade higher than the student Smith. So we first of all select grade from student where surname equals Smith. Literally look through your database and find the grade of Smith, say 52 for example. And that's all this will return. It will return a number. Then select name from student where grade greater than the grade that we've just recovered. So if you think about doing the inner part before the outer part, it maybe makes a little bit more logical sense. The join keyword allows us to join 2 tables with a foreign key and retrieve records from both. Select field names from table 1, join table 2 on table1.fieldname equals table2.fieldname. So again, that structure might be a little bit clumsy. You might just have to write it out a few times to memorize it. But the key point is you're linking the foreign key there. You're saying there is a field in table 1 and a field in table 2 that join together. They have the same information. They can have different names, that's fine, but you just have to tell it to link them together. So the example is here, select student.surname, course.name, from student, join course on student.courseid equals course.courseid. So you can see you have the table name, dot, and then the name of the column, the name of the field. They don't have to be called the same thing. It might be student.courseid equals course.course number. That would be fine. Transaction processing. A transaction is just a change to the database. The database management system ensures that when a transaction takes place, the database changes from one consistent state to another. For example, when a transaction is taking place, a record may be locked to prevent another transaction from interfering with the first transaction. The ACID rules to protect the integrity of a database. We have atomicity, consistency, isolation, and durability. You're often asked about these in the exam, and the number of students who forget what the C means or forget what the D means is usually quite impressive. So just memorize these. Atomicity. The transaction must be completed fully. If it is not completed fully, it will not be recorded. Consistency. Any change must not break the database. It must be consistent with how it was before the change. Isolation. A transaction must be isolated and not interfere with another transaction. And durability. A transaction must remain in the database. Data integrity refers to the accuracy and reliability of data and is of prime importance in any computer system. Validation and verification techniques can help ensure data integrity. Referential integrity. The database is consistent and there are no conflicts between data stored in different tables. So every foreign key has a matching value to a corresponding primary key. Make sure you cannot delete records that are used by other tables. ensures there are no orphan records, records unrelated to another table when they should be. Record locking is used to lock a table in a table until a transaction is completed. If the transaction fails, the record is unlocked for the next person to access. Redundancy. Redundancies must be built into a database system for organizations such as hospitals, military forces, and banks, for obvious reasons. This means they will have multiple cloned databases running at the same time that are all mirror images of each other, and these databases should be held in geographically remote locations to prevent catastrophic system failure. Moving on again, we've got 1.3.3 networks. Networks are collections of connected computer devices. They've become important because of the need to communicate and share data. A central store of data enables all the users of the system to see the same up-to-date version of the data they need, allows the sharing of important resources, for example, printers or disk storage, easier to back up data held on central storage. Efficiency of network depends obviously on the network manager. If there is a problem within the network, shared resources may not be available. Performance of a network degrades or gets worse as traffic increases. And clearly you can have security concerns. Network hardware that you need to know about. NIC, a network interface controller or a network interface card, enables a computer device to be connected to a network. This could be a separate card in a big desktop, or it could be a little chip built into the motherboard for a tablet or a mobile phone or something like that. Switch connects wired devices on a local area network. Wireless access point or WAP connects wireless devices on a LAN. Router connects different types of networks together. We have different transmission media. Copper cables transmit electrical signals, typically used for Ethernet cables. Fiber optic cables are made up of many thin glass strands or fibers which transmit data as pulses of light. And we also have radio waves, which uses part of the EM spectrum to connect devices wirelessly. We have different ways of classifying networks. Let's have a look at extent. Local area network covers a small geographic area, for example, a building or a small group of buildings. The company that uses the network is responsible for the infrastructure. WAN, wide area network, covers a large geographic area, for example, a city, a county, a country, continents even. Infrastructure is provided by a large telecommunications company that lease or rent out access to the network to other businesses. PAN, personal area network, links personal devices such as phones, tablets, and other devices that people commonly have, typically using Bluetooth. You also have the idea of SANs and MANs, storage area networks and metropolitan area networks, but those terms aren't so commonly used anymore. We can also classify networks by topology. A bus topology attaches nodes along a common backbone. Cheap to implement, but if there's a problem with the backbone, the whole network fails. Not commonly used nowadays. Ring, the nodes are attached on a circular backbone. Data frames are sent in one direction. They pass through each node and are collected by whichever node is specified by the address data in the frame. Again, not commonly used nowadays. In fact, bus and ring haven't been commonly used since before I was in secondary school. But they're still on the syllabus. We still have to talk about them. A better way to connect our networks together is a star topology. Here, each node has a separate connection to a central switch or a hub. Typically a switch nowadays, we don't really use dumb hubs anymore. Relatively cheap to implement and robust. Cable failures do not affect the whole network, and is the most common topology in homes and offices around the world. Mesh, all nodes are connected to every other node. So it is extremely fault tolerant, but obviously doing this as a wired version would be extremely costly and complex. This is much more useful for wired networks, especially for networks where you have to have really good resilience. Network protocols. These define rules for data transmission between devices on a network. A protocol allows devices to exchange data with one another as long as they're following the same rules. A standard is a formalized protocol accepted by most of the parties that implement it. Without standards, only hardware and software made by the same company could be used together. Having official standards is very important for networks, but remember, not all protocols become standards. Common protocols that you need to know about are TCP, Transmission Control Protocol, used to ensure error-free transmission, IP, Internet Protocol, used to address and transfer packets across the Internet between routers, HTTP, Hypertext Transfer Protocol, for accessing and transmitting World Wide Web documents, HTTPS, Hypertext Transfer Protocol Secure, a secure encrypted form of HTTP, FTP, File Transfer Protocol, for transferring files from one computer to another, SMTP, Simple Mail Transfer Protocol, for sending and managing emails, POP, Post Office Protocol, for retrieving and managing electronic emails, and IMAP, Internet Message Access Protocol, a more advanced protocol for retrieving emails. Protocols and layering. Network communication is very complex. We cannot have only one set of rules, one protocol to handle every aspect of network communications. However, a problem can be broken down into components, each of which is easier to solve than the whole. This has led to the concept of layering, whereby different aspects of a network's functionality are conceptualized and developed separately. Each component part, called a layer, concentrates on one aspect of the network without worrying about the others. So for example, here we have a typical model here. We've got the application layer, the transport layer, the internet layer, and the network or link layer. So this is the TCP IP model, TCP IP suite, that is kind of the basis for how we transmit data across the internet. The application layer is concerned with the production, communication, and reception of data. It governs how data moves in and out of applications. The transport layer is concerned with the establishment and termination of connections between network entities via routers. It is responsible for providing a reliable flow of data across the network. The internet layer is concerned with providing links between different network types, essential features of the internet that allows interoperability between all connected systems. And the network or link layer passes data onto the physical network, for example, copper wire or wireless radio waves. So again, the TCP IP is the most common set of protocols. It's used to bring the internet all together as well as private networks. It basically allows you to get data from point A to point B nice and easily. And you can see the idea is we've got the application layer, transport layer, internet layer, and then the bottom layer here. But we can have different protocols in different layers. So we could have HTTP as the application layer, or if we need an encrypted connection, HTTPS. We can have Ethernet at the bottom, or we could have a Wi-Fi protocol, for example. And we can upgrade the Ethernet protocols or the Wi-Fi protocols over time without having to swap out any of the other protocols being used at different layers. The domain name system, DNS, matches domain names to IP addresses using domain name servers. So for example, we can take a domain name like example.com and translate that into an IP version 4 or an IP version 6 address. Remember, we need URLs, Uniform Resource Locators, the full web address, because it's easier to remember than an IP address. People are very bad at remembering long strings of numbers. Domain names are constructed from a hierarchy. So again, you can see the example there, like bbc.co.uk, for example. Circuit switching, the establishment of a physical connection between two communicating entities. It provides an exclusive dedicated channel. The channel remains open for the duration of the communication session. So circuit switching is like when you watch an old movie and somebody makes a phone call. They go through to the lady at the circuit exchange and tell her which phone number you want, and then she makes an actual physical connection by moving those wires across. Not really suitable for the modern internet. You can't really do that every time you want to log into your social media. So we use packet switching, which divides a message into data units called packets. Packets are sent across a network by whichever routes are available or most efficient, and this is what we use for modern computer networks. Authentication. Most networks are protected by users having a username and password. These can be cracked quite easily by simple methods such as asking someone for them, social engineering, or simply guessing. You can also have a brute force attack where you just try every combination. 2FA, two-factor authentication. In addition to the above, We can send a code to a phone or use a special security device. I'm sure most of you are familiar with two-factor authentication nowadays. We also have the use of biometric information such as fingerprints or iris scans or face scans as well. Firewalls monitor and filter data coming into and out of the network. Again, remember, this is both ways. Often the exam students just write one or the other, but it's coming into and out from a network. Can be hardware or software or a combination of the two, and can use techniques such as IP address filtering, packet filtering, and port blocking. And obviously we've got encryption we've mentioned before, but sensitive or private data should always be made unintelligible to unauthorized individuals before being sent across a network. Proxies, these are computers that are interposed between a network and a remote resource. So there's never a direct contact between the user's computer and the remote resource. Everything goes through the proxy server. VPN, or Virtual Private Network, uses encryption to extend a private network across a public network. Corporations often use this to allow the people who work for them to use a wide area network as if it were a local area network. Can circumvent geo-restrictions and censorship, protect personal identity and location, and help to stay anonymous on the internet. Moving on, let's take a look at network architectures, starting with client-server. Client-server is a model where one entity, the client, requests resources and services from another called the server. The advantages of client-server network architectures. Client computers need not be expensive or powerful. It is easier to make data and often software accessible from anywhere in the network. Easier maintenance, easier for backups. Banks of servers can be combined to make the best use of potential. Resource-intensive activities can be devolved to a high-end machine. Easy monitoring of system performance, amongst others. Disadvantage: cost. Servers can be expensive and require specialist staff to set up and maintain. If the central server fails, it would bring down the whole network. In contrast, we have peer-to-peer. In a peer-to-peer network, all computers have equal status. Each computer on the network acts as both client and server, depending on circumstances. The advantages of peer-to-peer include the fact that it's cheap to set up as there are no additional hardware costs, and robustness as there's no single peer that can bring down the network. Disadvantages include if a peer goes offline, the resources stored on that device cannot be accessed, and there's no central maintenance. You can't update software centrally, you can't back everything up centrally, etc. 1.3.4 Web Technologies. There are three main elements to web pages: HTML, hypertext markup language, for content and structure; CSS, cascading style sheets, for presentation and formatting; and JavaScript, to add interactive elements. So here, straight from the exam spec, is everything you need to know about HTML. So you need to be aware of these to be able to read them and be able to code them if required. Again, it does say any other additional HTML tags will be explained within the question itself. So here is a very simple web page that uses all of those. So again, this is about as complex as the HTML will be. So if you understand this and you can code it, you're all good. And if we were to render that in a web browser, we would end up with something like this. So again, not too advanced. It is a web page circa about 1997 that they're looking for. Again, CSS, this is what you're expected to be able to know in terms of the styling and formatting. So again, worth spending a bit of time on this because it's one of those situations, if it comes up in the exam, either you know it or you don't. And again, we've got some examples here of what it would look like, either embedded directly into a web page or with an external style sheet. And again, that would look something like this, which is perfectly hideous. JavaScript is, again, an interesting one because it's a fully featured language. What you need to know about JavaScript for the exam isn't that much. You need to be able to read some basic JavaScript, but if you've done any programming at all, JavaScript should be quite easy to follow. In terms of actually coding it, it's really about outputting something on screen. And you can see here there are three different ways of doing that. Any additional JavaScript will be explained in the question itself. You can see here we have a simple function to validate form. Again, even if you're not familiar with JavaScript, you can probably see how this works. So in the exam, you may have to debug it if there's an obvious error, or just read it and understand it. And then the rest of the page isn't too difficult. You can see there's a little bit to output the code as well here. And you just have to be able to really follow along with that in an exam situation. Search engines. They build up indexes of websites that can be searched quickly by various search algorithms. When a search engine indexes a page, a program called a spider or a crawler or a bot transverses the web. It takes each word in the document and it adds an entry for the page under the word in the index alongside the word's position on the page. PageRank algorithm, one of the most successful ways that search engines have been used to produce meaningful results. Basically, this is what Google came up with back in the day. This doesn't just look at content to assess relevance, it ranks possible web pages according to external links. The following factors may affect a website's PageRank ranking: the number of pages that link to the site, the page rank of the linking sites, the number of outward links from the site. The process can be applied recursively to get a fairly good estimate of how important a page is. Now, this is the original algorithm. You don't really need to memorize the whole algorithm. It's certainly never come up in the exam. But what they might ask you about is the damping factor, the D here. Okay, so the damping factor can be set between 0 and 1. The damping factor reduces the ranking on the assumption that a typical user will eventually give up clicking and represents the probability that the user will continue, and it's generally taken as being about 0.85. Client-side scripting. The code is run locally on the user's computer through a web browser. Transfers some of the processing load away from the server with related performance benefits. Input data can be validated by client-side scripts before being sent. This will reduce the likelihood of erroneous data being sent for the server to validate and process. Client-side scripting would include something like JavaScript. Server-side, the code runs on the website's server. Less security concerns than client-side scripts. Remember, it is vital to keep the data owned by an organization secure. SQL processes will largely have to be located at the server end. No sensitive data should be sent to the client where it could be intercepted and manipulated. While a user can view client-side scripts by inspecting the web page, server-side scripts are not visible to the user. This would include something like PHP. 1.4.1 Data types. Primitive data types. Every piece of data that is stored has a type. The type determines how it is stored and what you can do with the data. I will assume that if you reached A level that you are familiar with primitive data types, but just double check that you do know the definitions for character, string, Boolean, integer, and real. It is easy to make a mistake in the exam and you're throwing away kind of very simple marks to get. Another topic that you should be familiar with is representation of positive integers in binary. We should know that computers store and process data using binary numbers, bits. We only use 1 and 0 for the bits in binary. Each digit's place is multiplied by 2 as we move from right to left. So we start with 1, 2, 4, 8, 16, so on and so forth. The largest number that we can represent with 8 bits is 255, so we can represent 256 values from 0 to 255. And the largest value that we could represent, for example, with 16 bits is 65,535. Binary to denary conversion. What is the 8-bit binary number 1001101 in denary? Well, we just have to fill in our table. If it's an 8-bit number, it's from 1 to 128. We write out the ones and zeros. If there's a 1, that's a value that we need to add together. So in this example, it's 128 plus 16 plus 8 plus 4 plus 1 equals 157. Please don't get the values in the table the wrong way around. I've seen that happen more than once. Don't be that student. To go the other way, from denary to binary, essentially we're kind of reversing the process. I want to convert 75 to binary. I can just do this with a process of repeated subtraction. So start at the left side with the most significant bit, try and do a subtraction. If you can, add a 1. If you can, add a 0. And then just work your way until essentially you run out of values. So that's an example there of how we would convert 75 to make it 01001011. Getting a little bit more complicated, use of sign and magnitude to represent negative numbers in binary. Sign and magnitude is a method of differentiating between positive and negative binary numbers. The most significant bit determines whether it is a positive or a negative number. If the most significant bit is a 0, the number is positive. If the most significant bit is 1, the number is negative. Again, don't get that mixed up. So we can see here we've got an example for -3 and +7. We've got the value for 3 and then it's a 1 at the start, so we know it must be negative. And then we have the value for 7 and we've got a 0 at the start, so we know it has to be positive. There are two problems with sign and magnitude. Half's the biggest value that we can represent, and needing a sign and a value complicates doing the arithmetic. 2's complement, a much more effective approach. With 2's complement, we make the most significant bit a negative value. This changes the column headings for 8 bits, for example, to -128, 64, 32, 16, 8, 4, 2, 1. So if you have a look at this value here, 110, 11011, instead of being 128 at the start, it's a negative 128 plus 64 plus 16 plus 8 plus 2 plus 1, and that gives us a total of -37. Next up, we have the addition of binary integers. So nothing complicated here, just basic binary addition. What are the rules? 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 0, carry 1, because 1 plus 1 is 2, which is 1, 0 in binary, and 1 plus 1 plus 1 is 1, carry 1, because 3 ones is 3, which is 1, 1 in binary. Note, in the exam, don't just do a binary-denary conversion and then add them up normally. You must show evidence of knowing how to perform binary addition. You have to show your carries, and then you can do the conversion to double check, but you have to show you understand these rules. So we have two binary numbers here. We're going to follow those rules to add them together, bearing in mind when we add 1 and 1, we've got to carry 1 to the next column. Or if we've got 1 plus 1 plus 1 again, we have to carry 1 to the next column. Again, once I'm finished, I can do a conversion just to double check that I've got the right answer, but make sure you show this table and you show your carries. After addition, we have to talk about subtraction. Rules of binary subtraction are quite simple. 0 minus 0 is obviously 0. 0 minus 1 is the only complicated rule because then it's 1 and then you have to borrow from the next column, and we'll look at that in an example in just a moment. 1 minus 0 stays as 1 and 1 minus 1 is of course 0. So in the case of 0 minus 1, we have to borrow 2, which means we take away 1 from the next column. If the next column is a 0, we turn it into a 1, and this repeats until we encounter one that we can borrow. They kind of fall like dominoes. So if you look at this example here, starting with the least significant bit over on the right hand side, 1 minus 1 is of course 0. 0 minus 1 is our special occasion, so we say it's 1. We move along to the next column, we've got a 1 there, so we borrow from that, we make it a 0. 0 minus 0 is 0. We move along, again we've got 0 minus 1, so it's a 1. We go along to the next column to borrow a 1, but it's a 0 there, not a 1. We can't do the borrow. So we flip that 0 into a 1, and then move along to the next column, and then take away the 1 from that column. We borrow it from there. Going back, we end up with 1 minus 0 is 1. 0 minus 0 is 0. 1 minus 0 is 1. And 1 minus 0 is 1. And that gives us our final answer. Convert positive denary integers into hexadecimal. What is 1461 in hexadecimal? We're just dividing by 16 and keeping the remainder. So 1461 divided by 16 is 91, remainder 5. 91 divided by 16 is 5, remainder 11. Remember, 10, 11, 12, 13, 14, 15 convert to A, B, C, D, E, F. So the 11 becomes a B. 5 divided by 16 is 0, remainder 5. Therefore, if we put the remainders together, we get a final answer of 5B5. Converting hexadecimal to denary. What is 2, 3F in denary? We convert 2, 3F into denary values. So that's 2, 3, which stay the same, and then the F becomes 15. And then we do a calculation. So in this example, we're going to start with this table here. And the first column is 16 to the power of 2, 16 to the power of 1, and then 16 to the power of 0, which is just 1. So we have 2 times 16 is 512. 3 times 16 is 48. 15 times 1 is 15. Put all those together, we get 575. Convert binary to hexadecimal. Super easy. We divide it into nibbles, so 4 bits in each nibble. And we lay out the table like this, 1, 2, 4, 8, and we just add all the values together. So 0, 0, 1, 1 is just 2 plus 1 is 3. And then we have 1, 0, 1, 0, which is 8 plus 2, which is 10. 10 we have to flip over because it's hexadecimal, and that becomes an A. So we have 3 and A. Convert hexadecimal to binary. So let's convert C6 to binary. First convert to denary, and then convert each denary number to a single nibble. C becomes 12, which in a single binary nibble is 1100. 6 stays as 6, so that's 0110 in binary. Put them together for our answer, 11000110. Representation of floating point numbers in binary. Real numbers are represented in floating point form using a mantissa and an exponent. The mantissa represents the significant digits. The exponent represents the power of 2 the mantissa is raised to. The exam questions will tell you the size of both the mantissa and the exponent. Please make sure you read that carefully. Example, the following 8-bit number has a 5-bit mantissa and a 3-bit exponent. So the number we're given is 0.110110. Our mantissa is 0.1101. Our exponent is 2. Move the binary point 2 places to the right and we get 11.01, which is 3.25 in denary. Remember, if the exponent starts with a 1, move the binary place to the left instead. If the first bit of the mantissa is 1, then it is a negative number. So our example here is 10101011. We convert the mantissa to side and magnitude form by reversing the 1s and 0s and adding 1. So 01010 becomes 01011. That gives us a mantissa of 0.1011. The exponent is still 3. We move the binary point 3 places to the right to get 0101.1 or minus 5.5. Normalization of floating point numbers. In order to improve the accuracy, the mantissa should not waste bits by having redundant digits at the start of a value. For a positive mantissa, after the leading 0, the mantissa is floated so that the 0 is followed by a 1. For a negative mantissa, after the leading 1, the mantissa is floated so that this 1 is followed by a 0. This is done by adjusting the exponent. Once the binary point is floated to the right place, positive mantissas are padded with 0s, negative mantissas are padded with 1s. So using an 8-bit floating point with 5 bits for the mantissa and 3 points for the exponent, in the binary fraction 0.0011, we need to float the binary point 2 places to the right. So need an exponent of minus 2. In 3 bits 2's complement, minus 2 is represented by 110. 0.00111 is written as 0.1100110 in normalized floating point form. A normalized floating point number will always start with either 01 or 10, and that's sometimes an exam question. How do you know? Well, that's how you know. Some floating point rules, briefly. Negative numbers will always be stored in 2's complement. Positive numbers stored in 2's complement remain unchanged. If the mantissa or the exponent begins with a 0, then it is positive. If the mantissa or exponent begins with a 1, then it is negative. To perform 2's complement, hold the bits to the right of the first one, flip the bits on the left. To reverse it, do the same. Moving the decimal place to the right is the same as shifting a number to the left, and the mantissa will get larger as it has a positive exponent. Moving the decimal place to the left is the same as shifting the number to the right, and the mantissa will get smaller as it has a negative exponent. If we have more bits for the exponent, we lose accuracy, but have an increased range. If we have more bits for the mantissa, we increase accuracy, but have a reduced range. There is always a trade-off between the range and accuracy when choosing the size of the mantissa and the exponent. Floating point normalization rules. We normalize mantissas to maximize the precision accuracy of the value stored and to avoid multiple representations of the same number. You can spot an unnormalized mantissa because it does not begin with 0, 1 or 1, 0. To normalize a mantissa, we float the binary point left, right shift, to be in front of the first significant digit and adjust the exponent accordingly, which will be negative. If the mantissa is positive, we lose the extra zeros, and if the mantissa is negative, we lose the extra ones. We will need to unnormalize a mantissa if we want to perform an addition or a subtraction in order to line up the decimal places, thus making the exponents the same. When we unnormalize a positive mantissa, the value is padded with zeros to fill in the mantissa on the left. When unnormalizing a negative mantissa, the value is padded with ones to fill the mantissa on the left. Adding and subtracting floating point numbers. When adding and subtracting normalized floating point numbers, we need to undo the normalization of the mantissa. We need to make the exponents the same for both values, all the values, so that the binary point is in the same place. You could just change one of the exponents so that they are the same, but in exams this often leads to error because you shift it the wrong way. It is always better to unnormalize all of the mantissas. Using a 16-bit floating point number with 10 bits 2's complement, mantissa, and 6 bits 2 complements exponent to add numbers, we must match the exponent. So that's the next slide. So you have a look at this. If you follow the rules that I've gone through, that takes you through the whole process. We make sure we normalize it at the end, just to be sure. But if we follow this method, we should get the right answer. So again, this is adding it. Same idea if we do a subtraction. Again, we can use 2's complement there as well. Again, making sure we discard the overflow bit and make sure we normalize the answer. And always we can just kind of double check if we do a denary conversion just to make sure we do have it right. But do make sure you are showing enough stages. Often in the exam, if this is a 4 or 5 mark question, for example, you need to show 4 or 5 lines of working. If you're taking any shortcuts and skipping things over, you're probably going to lose marks. Bitwise manipulation and masks. Moving the digits in a binary number left to right is called a binary shift. Each time the value is shifted one place to the left, the number is multiplied by 2. So if we have 33 represented in binary and we shift everything one place to the left, you can see we now get 66. And of course, each time the value shifted one place to the right, the number is divided by 2. So for example, if we have 68 represented in binary and we move everything one place to the right, then we're going to get 34. Shifting the number left when the most significant bit is a 1 means that we lose 1, which results in an overflow error. Shifting the number right when the least significant bit is a 1 means that we lose a 1, which results in an underflow error and results in a loss of precision. Logical operations and masking. The ALU can perform bitwise operations using the standard logical operators NOT, AND, OR, and XOR. NOT is applied to each bit in the binary to reverse the value of that bit. So I think that's quite obvious there. For AND, OR, and XOR, the operation is applied to matching bits in 2 binary numbers, the operand and the mask, to determine each bit in the resultant binary value. So here you go, we've got it for AND, we've got it for OR, and we've got it for XOR. Again, you should be able to work that one out quite easily. Masking is a very important concept that allows the CPU to manipulate individual bits in the operand, checking for values, allowing bits through or blocking them. AND is useful for checking conditions stored in a binary value. Masking with a 1 returns the operand bit value. Masking with a 0 excludes the operand bit value. OR can reset individual bits in a binary value. Masking with 1 will always set the return bit to 1. Masking with 0 returns the original operand bit value. XOR will check that the 2 bits are not the same, that is, return 1 if the bits are different, 0 if they're the same. If both mask and operand are the same, it returns a 0. If the mask and the operand are different, it returns a 1. How character sets are used. One approach to representing text value is ASCII, the American Standard Code for Information Interchange. Each alphabet character, digits 0 to 9, and a selection of special symbols and control codes are represented by agreed binary patterns. The ASCII character set was originally based on 8-bit binary pattern using 7 bits plus a single parity bit, and was able to represent 128 characters with the values between 0 and 127. The extended ASCII uses 8 bits, so it can represent 256 separate characters from 0 to 255. Due to size limitations, ASCII makes it impossible to display the wide range of characters for other alphabets or symbol sets, for example French or Japanese. A more modern approach is Unicode. Unicode was originally a 16-bit code allowing for more than 65,000 characters to be represented. This was updated to remove the 16-bit restriction by using a series of code pages, with each page representing the chosen language symbols. The original ASCII representations have been included as part of the Unicode character set with the same numerical values. 1.4.2 Data Structures. Starting with arrays. Arrays are data structures which are fixed size, so they're static, and contain data of the same type stored in a contiguous block of memory. A one-dimensional array is a single set of data, a single row, which is easy to visualize. A 2D array is a set of data which can be visualized as a table structure with both rows and columns. Now, a three-dimensional array can be a bit more complicated because it's a collection of two-dimensional arrays, like a series of tables on top of each other, which can be a bit harder to visualize. Record. A record is accessed through an attribute. A record is an unordered data structure. Indices may be programmed to provide the data ordered on a particular attribute. The ability to access data through an attribute makes the record structure more user-friendly. The need to define all the attributes before use makes the record structure more complex to initialize. A list is an ordered data structure. A list is accessed through an index. The index indicates the position of the data in the list. Lists have no predefined number of elements. Not needing to define attributes in advance makes the list easier to initialize than a record. Accessing the data in order by index is straightforward to program. Tuple. A tuple is an immutable list. The data cannot be modified. Tuples are useful for data that must be accessed by index but must not be changed. Linked list. A list of data together with a set of links to sort the data on various factors. Data is stored in order it is input, and pointers are used to link the data in the desired order. A start pointer is used to identify the first item. A null pointer is used to identify the last item of data. A free storage pointer indicates the first available free location. The use of pointers means that, unlike arrays, data in linked lists do not have to be stored contiguously in memory. They're also referred to as being dynamic in that they can grow or shrink in size as and when necessary. Linked lists are commonly used data structures with benefits of flexibility and ease of use. They can be used to implement other data structures such as stacks and queues. Below is a list of animals that can be stored alphabetically through the use of pointers. Below is a list of animals that can be stored alphabetically through the use of pointers. So if you have a look here, we can see we're storing it platypus, dog, gerbil, so it's not alphabetical, but if you follow the pointers, then we do get this alphabetical order because the start pointer is pointing at 2, which is dog, and then we go to gerbil and then to platypus, so the order is still alphabetical. Adding data to a linked list. Additional data is inserted at the next available free node. So if we're adding elephant, elephant is added to the location indicated by the free storage pointer, which is 4. The free storage pointer is updated to the next location, which is 5. The location in the list is identified, it follows dog. The pointer for this location is updated to point to the location for the new data item, which is 4. And the pointer for the new data item is updated to point to the next item, 3. So if we want to delete gerbil from the list, dog points to node 4, which is elephant. The data at node 3 can be deleted. The node for the deleted item is added to the free storage location. In this case, it becomes the first available free location. Queues. Data is added to the end of the structure. Data is removed from the start of the structure. Queues are a first in, first out data structure. Queues can be implemented using other data structures such as arrays or linked lists. In either case, 2 extra pointers are required to identify the front or the head of the queue and the rear or tail of the queue. Queues can be both static and dynamic. Several operations can be carried out on queues, so these could have different names in different scenarios, but the idea is basically the same. We've got to enqueue, which adds an item to the rear of the queue. We've got to dequeue, which removes and displays the item at the front of a queue. We've got isEmpty to check to see if the queue is empty, and isFull to check to see if the queue is full. So you might be expected to use similar operations, similar functions, or you may have to code them depending on the type of question. Queues, of course, have a wide range of uses in computer science, including storing print jobs until the printer is ready to print, CPU scheduling, and breadth-first traversal of a graph. Queues can be both linear and circular. When an item of data is removed from the front of a linear queue, all the other items move up one place. This is only suitable in a small queue, otherwise data processing time can be excessive. When an item of data is removed from the front of a circular queue, the only processing required is to update the 2 pointers identifying the new front and rear of the queue. Stacks. Data is added to the top of the structure. Data is removed from the top of the structure. Stacks are a last-in, first-out data structure. Push is the command to insert data. Pop is the command to remove data. Stacks can be implemented using other data structures such as arrays or linked lists. In either case, an extra variable is required to identify the top of the stack, a top pointer. The most common use of stacks is to reverse the order of a set of data items as they are popped in the opposite order that they were pushed into the stack. Problem with stacks and queues. A stack or queue cannot grow indefinitely. If you try to push more data into a structure, you can get, for example, a stack overflow. When this happens, it often causes the program to crash. Obviously, it's up to the programmer to ensure that this doesn't happen. And it can be the same if your stack or queue is empty and you're trying something like a pop operation. We can get an underflow, and again, this can cause the program to crash. Therefore, the programmer should check that the structure is not empty before attempting to do this. Trees. For data that does not fit into a list, for example, the directory structure on a computer hard disk drive, we need hierarchical data structures such as trees. The node at the start of the structure is called the root node. The nodes immediately down from another node are called children. The nodes with children are called parents. The lines that join the nodes are called branches. Binary trees. One specific kind of tree is the binary tree, where each node is only allowed to have 2 children. Each node contains a left pointer, data, and a right pointer. For an alphabetical list, if the next name is higher in the alphabet, go right. If it is lower, go left. For numbers, this means the left subtree contains numbers less than the root, and the right subtree contains numbers greater than the root. There are 3 ways to navigate or traverse a tree data structure: pre-order, in-order, and post-order. In order, in this traversal method, the left subtree is visited first, then the root, and then the right subtree. So you have a look at this tree here. If we do in order, it would go A, B, C, D, E, F, G, H, I. Oh, nice and simple there. Pre-order. In this traversal method, the root node is visited first, then the left subtree, and finally the right subtree. So again, with this example, we would have F, B, A, D, C, E, G, I, H. And finally, post order. Here, the root node is visited last, hence the name. First, we traverse the left subtree, then the right subtree, and then finally we go to the root. So here we would get A, C, E, D, B, H, I, G, F. Graphs. Graphs are data structures used to represent data items which have connection between them, such as locations on a map or products on an e-commerce website. The data nodes are called vertices. The connections are called edges. Edges may be assigned weightings. A graph may be directional or undirected. In a directed graph, the data connection may flow in one or both directions. In an undirected graph, the edges are all bidirectional. There are 2 methods of traversing a graph: depth first and breadth first. Depth first tree traversal. Depth first traversal involves traveling down one route as far as possible before reversing and traveling as far down the next route as possible. So with this list of nodes here, we would get A, B, E, C, D, G, F. With breadth first tree traversal, this involves visiting all the adjoining nodes for each node in turn. So for this, we would have A, B, C, E, D, F, G. Hash tables, a data structure that can map keys to values. A hash table uses a hash function to compute an index, also called a hash code, into an array of buckets or slots from which the desired value can be found. During lookup, the key is hashed and the resulting hash indicates where the corresponding value is stored. Hashing is an example of a space-time trade-off. Collisions. A perfect hashing algorithm will generate a unique index. Should this not be the case, a collision will happen. When a collision occurs, a rehashing algorithm can be used to determine the next available slot in which to store the data, or the data is stored in a linked list starting at that location. Moving on to 1.4.3 Boolean Algebra. Now, I'm not going to try and teach you in this section how to do Boolean Algebra. It's just a revision, some key points about these topics that you should know or refresh yourself on before your exam. So starting with our logic gates here, we've got a nice table here. We've got our ands, our ors, etc. all listed. We've got the logic gates, the notation, examples, truth tables, pretty much everything you can need to know about simple logic gates here. A half adder is a logic circuit with two inputs and two outputs. The sum and the carry where two inputs are added in binary. So you have to be able to recognize this. You need to know the truth table. You need to know the logic gates, etc. We put these together, we can get a full adder. A full adder allows the carry from a previous calculation to be carried forward in the calculation. We now require three inputs, one for A, one for B, and one carried over from the previous column. This can be done by using two half adders and an OR gate. Flip-flop. These circuits are capable of storing information, for example, RAM memory. A flip-flop can store one bit of information. Flip-flop circuits are combined to make a range of other flip-flop circuits. The next one we need to know is the type D, the D-type flip-flop. Two flip-flops combine to make a D-type flip-flop. The D-type flip-flop delays the signal by exactly one clock pulse. It has two inputs, data and a clock, and outputs the data and the inverse of the data. So Boolean algebra. So here are the various laws and rules that we need to know about. We've got De Morgan's law, distribution, association, commutation, double negation, and absorption. Again, you need to be familiar with these as a nice way of simplifying your Boolean algebra and solving those problems. We've got another couple of tables here just to help you out. We've got some AND rules and we've got some OR rules. Again, you can pause this and review. Carnot maps. Again, very useful for simplifying all these expressions. Carnot maps are a modified form of truth table optimized to enable pattern recognition to be used when identifying minimal logical expressions. Carnot maps are maps of possible inputs and mapped against the required outputs. So I'll just give you some simple examples just as we review this. A two-input example, nice and simple there. You can kind of go through that and double check everything. Three-input example here as well, just to show you an example of that. And a four-input example to get a little bit more complicated. But again, very useful for simplifying. 1.5.1 Computing-related legislation. The Computer Misuse Act of 1990. Under this, it is a criminal offense to make unauthorized access to computer material with intent to commit or facilitate commission of further offenses, with the intent to impair or with recklessness as to impairing operations of a computer. So hacking, creating or spreading viruses and other malware, stealing information for the purposes of blackmail, etc., now became illegal in the UK. The Data Protection Act, originally from 1998, strengthened in 2018 with the introduction of the General Data Protection Registration, or GDPR. The purpose of DPA is to control the storage of data about individuals. It makes a data controller responsible for the accuracy and security of data kept by an organization about the data subjects. And there are 8 key principles. 1. Data must be used and processed in a fair and lawful way. 2. Data must only be used for the stated purpose. 3. Data must be adequate, relevant, and not excessive for the specified use. 4. Data must be accurate and kept up to date. 5. Data should be kept no longer than necessary. 6. Data should only be used according to the rights of the data subject. 7. Data should be kept safe and secure. 8. Data must not be transferred to organizations within other countries that do not offer a similar level of protection. The Copyright Design and Patents Act of 1988 protects the intellectual property of an individual or organization. It grants automatic copyright to anyone who has created creative work, whether physically or digitally. Under the Act, it is illegal to copy, modify, or distribute software or other intellectual property without the relevant permission. And that brings us nicely on to Creative Commons. Creative Commons is a licensing framework which allows content producers to publish their intellectual property with licenses that give permissions for others to use their work. Under such licenses, the author may choose to allow complete access for non-commercial use only, allowing redistribution of the work, providing the user abides by certain conditions. So if you've created a work and you want people to use it in certain ways, you can use a Creative Commons license to give some rights up and allow people to have some kind of creative use of your work, but with conditions attached. Regulation of Investigatory Powers Act 2000 gives certain bodies the rights to monitor communications and internet activity. This was prompted by an increase in criminal and terrorist activities on the internet. RIPA provides certain public bodies such as the police and other government departments with the right to demand ISPs, internet service providers, provide access to a customer or customers' communications, allow mass surveillance of communications, demand ISPs fit equipment to facilitate surveillance, demand access be granted to protected information, allow monitoring of an individual or individuals' internet activities, prevent the existence of such interception activities being revealed in court. And moving on to the final topic, 1.5.2, moral and ethical issues. So this is a fairly large scale section. I'm just going to go through it very quickly. You do need to be reading around this, looking at news stories and news events, making sure you're well informed so that you can answer these longer essay questions on these topics. Computers in the workplace. Computer technology in various forms plays a major part of the workplace. Computer technology has changed the skill set required for the modern workforce. So we need more programmers, more analysts, more technicians, etc., but less secretaries, clerks, factory workers, etc. A workforce may be subject to monitoring by computer technology to assess their productivity, the way they work, and their effectiveness. The advantages and disadvantages of this issue depend on the type of industry and, of course, whether you are an employer or an employee. Remember, there's always advantages and disadvantages for every issue. Automated decision making. Automated decision making is used where the amount of data or the response speed makes it impossible for a human to react effectively. Computers use algorithms to process the data and reach decisions. The quality of the decision will depend on the accuracy and completeness of the data, the predictability of the situation, the quality of the algorithm. Artificial intelligence, AI, ChatGPT, and all that other stuff, sort of good stuff. AI programs learn from experience. They're often based on the expert system model with a knowledge-based inference engine and a user interface. Many low-skilled jobs have already been replaced by machines, for example, robots in a car manufacturing factory. Machines can do dangerous jobs in hazardous environments. They can do boring and repetitive jobs, and they never get sick or go on strike, and they can work 24/7. Many experts, however, believe that AI systems are going to begin to replace humans in mid-level jobs, and to a certain extent you can already see that in some industries. AI has advanced to perform some tasks that experts believed would be impossible a few years ago, for example, beating top human players at the game of Go. Environmental issues. When our computer device stops working or when we simply want a newer device, old tech is simply thrown away. This is called e-waste. These devices often include toxic materials that can leach into soil and contaminate water supplies over time. Although modern computers consume low levels of electricity individually compared to older machines, collectively there are billions of more devices being used now than in the past. Data centers, cryptocurrency miners such as Bitcoin can use massive amounts of energy worldwide. There are, however, positives for the environment. Communications sent electronically do not waste paper or ink. People who work from home, which is made possible by computers and networks, do not have to burn fossil fuels driving their cars to work. Industrial processes that are computer controlled rather than overseen only by humans can be more efficient and therefore cause less pollution. Censorship. Internet censorship is the deliberate suppression of what can be accessed or published on the internet. Governments or organizations may impose these restrictions for various reasons. To limit access to socially unacceptable material, to limit access to what they regard as dangerous information. Of course, what one person regards as socially unacceptable or dangerous is not what another person regards as. Monitoring behavior. People are increasingly being monitored by computer technology. Your search terms are tracked and often used in marketing. Websites you have visited can track your internet history using cookies and similar technology. Purchase items are often recorded and sold to advertisers who might wish to advertise similar products to you. Social media posts can be viewed by employers and the press. Internet activity at work can be monitored by employers. Employers can monitor performance using special monitoring tools. Urines? Special monitoring tools? Okay, that's funny. Using is much better. People leave a digital footprint wherever they go. Mobile phones can track our locations, store credit cards, record our shopping habits, etc. You've got GPS as well, which gives you physical locations of where people are all throughout the day. And CCTV is everywhere, and facial recognition is improving all the time. Analyzing personal information. Analyzing large amounts of data, including personal data, reveals patterns. These patterns can be of shopping habits, social activity, criminal activity, information to inform business strategies, or the development of new medical treatments. Data mining is an automated process that searches for patterns in large data sets to predict events. In business, it is used to identify patterns to inform strategic business decisions. The data can be used to predict future sales and effective and targeted marketing strategies to improve business profitability. Layout, color paradigms, and character sets. Content on the internet should be suitable for as many people as possible internationally. The layout, use of color, and choice of character sets should all be carefully considered. Layout. English language readers read from left to right, so important information will often be on the top left of a web page. But other cultures read from right to left. Color paradigms. Different cultures have different associations with color. So in China, red signifies luck, while in the UK it indicates danger. Different languages use different character sets to allow for any additional letters or symbols used in their alphabet. So there we have it, the end. I've tried to go through as much as I can, as fast as possible. There's some topics I'd love to extend, but then we'd end up with a 3 or 4 hour video, which is probably impossible for me to get done and edited before your exam. So I think this is probably going to clock in at about 2 hours. I just need to go edit it and put it all together now. I hope it was of some use to you in some way. All the best of luck with your exams. See you in the future.